Identifying bad characters. Welcome back, and congratulations on making it this far. In the previous lesson, we achieved a major milestone redirecting program execution by inserting a reliable jump ESP instruction into the overwritten EIP. With that in place, we now stand at the doorway to arbitrary code execution. But before we can inject and execute shellcode, we must tackle a subtle and often overlooked problem that has broken more exploits than any other. Bad characters. What are bad characters, and why do they matter? A bad character is any byte value that interferes with the correct transmission, interpretation, or execution of your shellcode or payload. These characters can terminate strings prematurely, like x00, be interpreted as control characters such as x0a, x0d, cause data truncation, corruption or misalignment, get stripped or modified by the target application before reaching memory. In short, a bad character is any byte that doesn't arrive in memory as you sent it, or causes your payload to break when it executes. And here's the catch. Bad characters are specific to the context of the vulnerability. The same byte that causes issues in one program may be perfectly safe in another. This means you cannot rely on generic lists. You must test, verify, and eliminate bad characters for each exploit you write. Today, our objective is to prepare a comprehensive list of byte values from x01 to xff. Inject that list into the payload space. Observe how it appears in memory post-crash. Identify any characters that are missing, altered, or truncated. Eliminate them from future shellcode and payload encoding. This process ensures that when we finally insert real shellcode, it won't be corrupted or broken by unsafe characters. I already have a full list of hex characters in my home directory. I'll begin by copying this file into our stack folder. Next, we'll incorporate this list directly into our exploit skeleton by defining a new directive named badchars. We intentionally omit x00, as null bytes are universally problematic in null-terminated string environments. And the same thing for x0a and x0b, which may also be interpreted as line-breaking or passing control characters. This byte sequence will be injected into memory immediately after the EIP overwrite, precisely where our shellcode will eventually reside. By monitoring which characters survive intact and which are corrupted or truncated, we can determine which bytes are safe to use in our final payload. We now adjust our exploit skeleton to insert the badchars block right before the trailing junk section. This way, the bad characters are clearly isolated for memory inspection post-crash. Once the file is updated, go ahead and save and exit. On the Windows XP machine, I will begin by deleting the old .ssa subtitle file. Then I will download the newly generated one from our exploit development environment. Next, I'll launch VLC through Immunity Debugger. But before loading the subtitle file, I'll place a breakpoint at the appropriate location, allowing us to pause execution right before the vulnerable parsing routine is triggered. Once the setup is ready, I will load the .ssa file and wait for the crash to occur. When the application halts, press Shift F7 to step into the crash context, and then follow ESP in memory by right-clicking and choosing Follow ESP in dump. Now comes the detective work. I will carefully examine the hex dump. We're looking for anomalies in the byte sequence, indications of which characters were altered, stripped, or misinterpreted. For example, if I see something like 2A2B002D2E, it is an indication that the byte X2C is missing and has been replaced by X00. That suggests X2C is a bad character, one that the parser or underlying Windows file system cannot process correctly. Once we identify such characters, we need to go back to our script and update the bad chars list accordingly. Then, regenerate the .ssa file with the updated set of characters. Proceed to download it again to the target machine, and repeat the test. Let's inspect again. We can now see that the full modified list appears intact, with no missing, replaced, or corrupted bytes. I can confidently say that we've identified all problematic characters. This gives us a clean encoding space, and that's essential. It means we can now safely encode our shellcode with confidence that it will arrive in memory and execute as intended, without being broken during transmission or parsing. You might be tempted to skip this phase, thinking, can't I just rely on the default list of known bad characters? That approach might seem convenient, until the day it silently breaks your exploit. An exploit that runs flawlessly in your lab but fails mysteriously on the real target. That's almost always a bad character issue. By verifying this up front, you save yourself hours, or even days, of painful debugging and unpredictable failures. A skilled exploit developer never assumes which bytes are safe. They test, they observe, and they verify every single time. Now that you've identified the safe encoding space, it's time to experiment and sharpen your instincts. 1. Try sending an unencoded payload that includes X0A, which stands for new line. What happens to the rest of the buffer? 2. Add your bad character list to different parts of the buffer before and after the jump and see how memory alignment affects the result. 3. Explore how VLC interprets special characters by injecting control bytes into the header or subtitle metadata. These experiments will deepen your intuition for how input is passed, stored, and ultimately executed. In the next lesson, we'll use this clean buffer space to inject real shellcode and watch it execute. We're almost there.